about common mistakes in data analysis and talk about some strategies to address them. So as Bob said, when we published this paper in 2010, we never expected that it was going to become one of the journal's top-cited and downloaded papers. I think it has been downloaded more than 22,000 times. So you may ask the question, why? And I think the answer is very simple. If you were to select a random papers from different journals, and if you were to reanalyze them, you will see common statistical problems, such as mainly violation of the assumptions. Now, depending on the assumptions that you're going to violate, you may have things like, well, you may increase type 1, type 2 error, and the thing is, you will end up providing wrong ecological conclusions. So, as you can see, we do a lot of teaching, and we have met people from different countries, different nationalities, and meaning people that have been exposed to different educational systems. However, what they have in common, they all complain about the same things, gaps and misconceptions. They even claim that the knowledge that they get at the moment of doing their undergraduate studies is not enough to finally fulfill the answers when they have to go through a PhD program. What is more important, and this is based on our experience, if you, when you teach statistics, if you show students typical numerical output from linear regression, as long as it is one covariate, they will all understand it. As soon as you add 2 or 3 covariates, interactions, factors with many levels, they don't have any idea what is going on. They don't even know how to reconstruct the equations and make predictions. They also have the tendency to ignore the importance of doing data exploration. I mean, they tend to jump immediately to a definite statistical technique. They, in most of the cases, they also ignore the most fundamental assumptions of all these statistical techniques. And the moment when you ask them, do you have any indication, can you give me some indication of model misspecification, they haven't even heard about things like model validation. Now, what is more important is that we, just by curiosity, we also ask them during classes, well, do you review papers? Most of them, they will say yes. Okay, how much do you spend on doing this? Well, between half a day or perhaps 1 day is maximum. Then you ask, do you like the statistical part of this manuscript? Well, they say no. Why is the case? Do you understand that? Not always. So that means the same people that are not able to understand numerical outputs are doing paper reviewing on a regular basis. So that is something that's the reason why we decided to go back to the basics and talk about data exploration. So if you can guarantee that you follow from A to Z the kind of protocol, then we think we can avoid doing type 1 and 2 errors and reduce the chance of making ecological, the wrong ecological conclusions, and at the end of the day, you can provide better recommendations. So what we did in that paper, we proposed a protocol where we include outliers. So we mention what to do if you have influential observations, how can a single outlier can highlight entire analysis, what happens if you have homogeneity of variances, do you need to apply transformations just to stabilize the variance, or can you incorporate heterogeneity in your model? We address some kind of misconceptions like normality. We talk about zero inflation. Also, when we talk about zero trouble, we mean not only in the univariate world, but also when you have to do multivariate analysis. Very important, it's something that is always ignored, collinearity. We talk about relationships, interactions linked to the story of low sample size, and very important, violation of independence. I don't want to spend much time explaining one by one, but I would like to put some emphasis and address 3 important items: normality, collinearity, and interactions. When we say normality, I would like to address some misconceptions. And why we talk about misconception? Because when you teach statistics, or even when you review papers, people think that as long as you talk about statistics, the only thing that you have to check or be worried about is normality. And you always see this type of statements in paper. We have checked data for normality before doing the analysis. During the classes, we ask the students, do you think that normality is important? They all say yes. And then you ask them, do you check normality on the raw data or do you check normality on residuals? And they say, we don't know. So I have an example here. This is a data set that comes from Dr. Graham Pierce from the University of Aberdeen. Here we have the GIS distribution on squid data. I don't know if we have here fisheries biologists, but GSI is gonadosmotic index. Is a ratio between the total weight of the gonads divided by the total weight of the animal. And they want to analyze this, taking into account 3 covariates: the sex of the squid, different fishing locations in the North Sea, and different month. So you may think about something like 3-way ANOVA will be a starting point. Now you show this picture to students and they will all come up with the idea of normalizing the data. Apply a transformation to make this normally distributed. So let's forget about that. I always tell them, what if we split up the data into 2 different, based on sex, 2 different pictures. So we have the distribution for the GSI for the females and then the distribution for the males. What you can see clear is, in this case, is that it's a clear difference in the shape and center of the distribution. I'm pretty sure that factor sex is going to be important in this analysis. Now, what if you apply transformation on the raw data? Then the consequence is that you can destroy the sex effect. So what we learn from here is that we shouldn't put emphasis on applying a transformation on the raw data. Maybe we should let the covariates explain this non-normality behavior that we could see at the beginning. And finally, we should be able to check the assumption based on residuals. But this is something that we still see when we review papers, this type of misconception. Then the other thing I would like to put emphasis on is collinearity. And this is frequently ignored by ecologists. Now, when we talk about collinearity, we mean relationships between covariates. And the consequence is that p-values can be blown up in the presence of variables that are highly collinear. Things like the length and the weight, if you use them as covariate, matter, organic material. Those are typical examples in nature that you know a priori that you're going to have this problem. Now, depending on the quality of the data we have, we try to target this problem from different angles. Either you use PCA by plots, because it works on correlation metrics. You use variance inflation factors. You do simple conditional box plots. Or you just look at Pearson correlations and pair plots. That's the one I would like to show right now. Now, the general consensus is that you should be looking for very high Pearson correlations because that will be an indication for collinearity. That's true. But in this case, we have situations where what we're analyzing here is the distribution, abundance of a flat fish species as a function of 4 covariates. At the end of the day, we could only use 1 in the analysis. Because even though you could see that this Pearson correlation is not very high, well, but if you look at the relationship between depth and salinity, you can see there is a clear pattern between these 2 covariates. So be careful with these type of things. Another example where perhaps Pearson correlations are not very high, but you still have the same problem. At the end of the day, what we're measuring here is temperature, and only 1 covariate will do the job. Now, there's a very interesting case study I always try to explain to students. I took this data set from a publication. It has also been published in the book from Quinn and Kew. It's all about habitat fragmentation. So someone is looking at density of birds in different forest patches in Australia. They're using, so they tend to model density of birds as a function of 6 covariates. As you can see, we have, this is a categorical covariate, grazing level, and we have another one that says year since isolation, the year that the forest patch has been isolated from the rest. Now, if you make this relationship, and this is a typical simple conditional box plot, what we can see here is that forest patches that were isolated earlier in time also have higher grazing intensity. So the question that you're going to ask yourself, are we going to include collinear variables? Well, in reality, we should be able to make a choice, and it doesn't matter which covariate you're going to select in the analysis. Now, the typical reaction we have from students, everything I measure is important. Why? Because I've been spending 3 months collecting data. Why do we have to chop out variables? Well, okay, let's see what happens if you keep collinear variables in the model. What I have here, what I've done with this data set is just a simple multiple linear regression. Now, I'm not going to talk about p-value. This is the output from the drop one. I mean, for those that are users, this is we're just looking at the f-test. So I have, in the first output from the drop one, I have, you can see I have highlighted the p-values for these two covariates that are meant to be correlated. Here's in isolation and factor grace. So you see this one is a very big p-value, and this one is borderline significant. Now, what happens if we remove factor grace from the analysis? Well, the other one becomes highly significant. And the same would happen if I go for a third approach where I only include, I include a model containing only grace and the remaining covariates. So, question is, which variable is driving the system? So, is it grace? Is it years in isolation? Is it both? Well, unfortunately, you won't be able to answer that question. So, but the important thing is that even people that they are aware of this type of problems, they also write down in their own conclusions there is one covariate driving the whole system. And we have to be spot on these things. We have to be able to say that with the current data as it is, with this analysis, we won't be able to make that conclusion. I always make the same joke. What happens if you're going to say, if you're going to give recommendations to the government and you say that you have to stop doing farming activities and you're going to give money to the farmers, well, they may come along and will say, you cannot blame us because maybe that the reason why you don't have enough birds is because of the covariate years in isolation. So we have to be worried about that. Now, what is the solution? Well, we should be able to do a different experimental design. And sometimes, unfortunately, you don't even have the resources or the capacity to do that. In this case, we should have gone for forest patches that were isolated at the same time frame with different grazing levels. But with the situation that we have, maybe we cannot go back in time and we cannot go again and do the same analysis. Okay, I have tried to sketch this problem using multiple linear regression analysis, but whatever to do in terms of data analysis, doesn't matter whether you're going to go for a mixed modeling approach, redundancy analysis, any multivariate technique, any univariate technique, collinearity is always a problem and it's something that you have to consider. The other thing I would like to put emphasis on, because I have seen this problem very often in papers, is the problem of sample size whenever you consider using interactions. Okay, so everybody, I think, is familiar with the concept of interactions. We normally try to make exploration tools using co-plots, interaction plots, like for example this one, where we have richness of solventic species versus a covariate that represent the height of a site compared to the average sea level, and we have different widths from the same month. So if you look at this picture, because lines are not 100% in parallel, you may think about including an interaction. The problem is that sometimes, because you have in one specific compartment, you only have a few points, maybe one point is highlighting the entire interaction. So if you were to reanalyze this without the point, maybe things or parameters are not longer, or the interaction is not longer significant. The same happens with this type of situation. Sometimes people like to get very enthusiastic in the idea of including three-way interactions, and what happens is that you don't even have data in one specific combination. So I think that these tools are very handy and they should be done a priori before you think about including an interaction, just to check the quality of the data you have. Now here I have what is the consequence that you can make if you ignore these type of problems. So I have a data set that consists of oyster catchers. Actually what we have is shell consumed by oyster catchers in 3 different areas, 2 different months, and using 2 different techniques. These animals, they tend to force within the bulb, or they take, they hammer and they take the flesh. So I have three covariates. Maybe we can put a question that will be linked to the three-way interaction. So this is the relationship between shell length and feeding type change by mount allocation. So from the statistical point of view, you will be working towards a model like this. Three main terms, all the two-way interactions, and finally the three-way interaction. But let's say that you don't check the quality of the data you have. And let's say that you go immediately into the analysis. Well, I can show you the results. More importantly, the three-way interaction is significant at the 5% level. Then you have the p-value that most of the people would like to have. Now, if you do this, you can sketch results in different ways. I'm using a coffee plot, and it's quite clear that in one specific combination, so here we have large fitted values for this particular condition. So you do a model validation, you check for residuals, everything looks fine so far. You don't see any indication of any kind of violation. So you will be tempted to write down in a paper that you have a relative fitted values for the stubborns at location A in December. However, if you make a second picture, where I'm again trying to sketch the fitted values and I'm superimposing the raw data, you can clearly see that the whole interaction that we're talking about is mainly driven by two data points. So, two observations most likely are causing the three-way interaction to be significant. We can even look at the Cook distance plot and we don't see anything, any point sticking out. Now, we should have known this problem a priori. Just a simple table command will give us the indication that we have a real problem in terms of sample size, so we have only 2 or 3 observations for that particular fitting condition. I mention these things because when we review papers, we see this type of problems very often. So summarizing, before writing papers, try to fully understand every aspect of your data. And very important, try to be able to interpret the results from the statistical models. We always encourage people, instead of looking at those tables, because people tend to report these tables, the best way to understand those tables, what about sketching the fitted values? Make a nice picture and try to make sure that you can do a interpretation of your results. And that will mean that you will avoid giving the wrong ecological conclusions. Very often you see in papers that the results section is not matching what people write on the discussions. And that is because in many cases there is the interpretation from the results are really biased. So we have to be very careful about that, and we have to encourage people to put attention on all these different things. As to the first point, try to fully understand every aspect of the data. What we mean is that we should be consistent, start making all these different plots. In that sense, are fantastic because you can do whatever you want. You can do lattice pictures, ggplots, whatever, just to check for influential observations, do all these different plots to check for collinearity, have a look at relationships, check the quality of the data in terms of interactions where you have highly imbalanced data, yes, no, and there will be a point that you have now, or you're now in the situation to do some sort of brainstorming. This is what you think, and then based on what you have, based on the quality of the data you have, you can then think about doing linear regression, again, GLM, or NX modeling. I mean, at this point, you also think, something I haven't mentioned, but it's also very important, you also have to put emphasis on dependency among your observations. Every time we have to help students to do data analysis, one of the first questions we always ask, which rows in Excel do you think are going to be correlated? I mean, do you think that you have a situation where you have multiple observations from the same animal, the same physical unit, the same vessel, the same hive? Well, that will give you an indication that you have to include, highly likely, a correlation structure in your data. Otherwise, you will be violating one of the most fundamental assumptions in regression type techniques. So now, once you do your data exploration and you check for the quality of the data you have, then you can apply your model, ask yourself if everything is significant, do a model selection, I'm not going to talk about model selection. Mark has already mentioned the word model selection. So if you want it, you can go for model selection. You can decide what to do, whether hypothesis testing, AIC, BIC, information theoretic approach, whatever. But before doing anything else, before writing down a paper, go for a model validation, check all your assumptions, and then it's time to go for the model interpretation by perhaps sketching the figured values, and then you can go on and say, I can get my paper. If not, go back again and try to fix the problems that you may encounter. Now, sometimes it's difficult to convince the students to do the right thing. It's only when we say that academic career depends on paper that they wake up and pay attention. But if this doesn't work, I always show this slide to them, and I think they can get a bit more convinced, because here what I'm trying to sketch here is the story of two PhD students. One is doing the right thing, the other one is just collecting data, and he or she doesn't know what to do. Seriously, we've been in teaching in places where people were doing very important type of work, like assessing the quality of the food that we eat, or probably investing a lot of money and time in collecting deep sea water images, and then they don't know how to analyze that. So I think that after looking at this picture, we can all convince that we have to go back to the basics and make sure that we assess the quality of the data that we have before entering or doing any data analysis. Okay, thanks for your attention, and hope.
Okay, thanks for that talk. You got lots of useful advice, and some of which I failed to do. Actually, well, a lot which I failed to do. So, are there any questions? Do we have one from a statistician? Yeah? Yeah, sorry, yeah. A quick tap dance.
Yeah.
How do you think we can improve statistical training for undergraduate ecologists and biologists?
Well, I think you mentioned part of the answer. I think we should be putting emphasis at the undergraduate level, because all the experience I collected, all the things that I've been mentioning, happens when you teach PhD students and postdoc. But the whole thing should start before. And so we have to make an effort in that sense. At the same time, we have to be aware of who is going to review papers, because if you're not familiar with all these techniques, then you shouldn't be able to review the statistical part of the paper. So I think that we should be putting emphasis at the undergraduate level. We should be thinking on when we should be teaching statistics, because what you see normally, what people complain, students complain, is that they have a model of statistics at the first year, but they don't have any data set of their own, so they don't know how to analyze the data. And by the time they really face those problems, or when they are starting to do the MSc program or project or the PhD thesis. So I think that we should be putting emphasis at that undergraduate level, and make sure that we are going to teach the techniques that nowadays people need to use in the moment of doing or analyzing ecological data. Because what you see in those programs is that they will take it over up to the point that you have things like t-test, chi-square test, and if you're lucky, one-way ANOVA. But then there's a whole world around that. There is life behind t-test, chi-square test, and you need all this stuff to analyze the data. So I think that is where we have to put the emphasis on.
Okay, thanks. A quick question. Do you want to? Keen.
Sort of following on from that, do you think we should be teaching undergraduates sort of point and click methods, so you focus perhaps on the concepts, or do you think we should be perhaps teaching them a bit more of the sort of the maths and the sums underlying it, so that they actually understand some of the details of the tests?
Well, that is also an interesting question. I think that they should have a kind of working knowledge, so you have to go into the mathematics up to a point that they can comprehend. But keep in mind that it will also depend on the country. There are countries where people can drop mathematics when they are 16, 14. And that happens to us. Sometimes you show a matrix algebra and they ask you, what is that? We haven't seen this before. So I think that we have to give them the working knowledge, go a little bit deeper, but not put a lot of emphasis in doing demonstrations where these values come from. So I think we have to find a compromise in that sense. Because of course you have to apply a technique and you have to be familiar with that technique. But we don't need exactly to go very deep into those mathematical details if what they're going to do later on is just to make sure they're going to do a good application. So it's a little bit in between, I would say. And based on our experience, that is the best way that things will work.